Good morning, good afternoon, and good evening to all the attendees, and welcome to IEEE Sensors tutorial. I'm Gayathri Pillai, a faculty member at Center for Nanoscience and Engineering in the Institute of Science, Bengaluru, India. Today, I will be giving a brief tutorial on Piezoelectric MEMS resonator technology. This talk is divided into three sections, namely Introduction to Piezoelectricity, Piezoelectric MEMS Resonators, and a very small discussion regarding the applications. So let us start with the Introduction to Piezoelectricity. This slide is used to emphasize the wide spectrum of applications that are enabled using PiezoMEMS technology. Starting from the very low frequency applications such as energy harvester, where a MEMS device is deployed to convert the vibration of the environment into electrical signal, which is eventually stored. Accelerometers are units which are used to monitor the acceleration of the system and are often deployed for machine health monitoring, car safety applications, etc. Small-scale robots, which are mechanically versatile, are used for high-impact conditions, and this is being demonstrated using PVDF. Here they are used, the project that this can be used in hazardous environments and also for rescue applications where it is impossible to send a human being. Magnetometers are inertial measurement units used to monitor the variations on the magnetic field. Thin film PMUTs are one of the highly successful research and also industry throughput domains where ultrasonic waves are used for non-destructive sensing. Among many other applications, they are used for imaging, range finding, fingerprint sensing, etc. Vesper has demonstrated microphones and they are implemented using piezo materials as well. Now, this is an example of pressure sensor where different pressure coefficient of frequency of the modes are utilized to realize pressure sensors. Here, surface acoustic wave-based devices are shown. Support transducer topology has been used to excite high-Q bulk modes, and they are deployed as rotation rate sensors, also known as gyroscopes. Mass sensors, whose readout mainly depends on amplitude ratio and frequency variation, has been widely adapted in PiezoMEMS for environmental sensing applications. PiezoMEMS are commonly used for PM2.5 pollutant sensing. Resonators with metasurfaces on the top of the electrodes, or a metasurface, as you can see over here, we have nanoplasmonic metasurface, are used to attain wavelength selective infrared sensors. Next on, an application of SAW for biodiagnostics is shown where acoustic waves are used for cell sorting applications. Oscillators are one of the major research and business arena for piezo technology. This is an example of a bulk acoustic wave resonator used as a building block in the oscillator system, and it is demonstrated by Texas Instruments. Low loss delay in the gigahertz range have been successfully demonstrated using materials such as lithium niobate. FBAR-based filtering solution is one of the biggest success stories of piezoelectric MEMS technology because we all use these filters in a modern handset, and it is in itself, the filter itself is $1 billion industry. The applications of piezoelectricity has advanced by leaps and bounds, and it is being currently investigated for applications such as phonon cavities for quantum communication application. So this one slide shows the importance of PiezoMEMS technology and the wide area that it covers. To understand it better, let us have a look into the basics of piezoelectricity. So this is the part 1 of the tutorial where it has been divided into 3 sections. First, we will understand the origin of piezoelectricity and then move over to the piezoelectric coefficient and finally overview the different piezoelectric materials that are used in industry, academia, research institutes, etc. So let us begin with a thermodynamic analysis. Consider a material which has no stress acting on it. And in some of the piezo materials, the center for the positive and the negative charges coincide in such a scenario, and there is no net charge generated. However, when an external field is applied to the crystal deforms and it leads to a net charge generation as the positive and the negative centers do not coincide anymore. And thus we can primarily conclude that crystal asymmetry or non-centrosymmetric nature is a requirement for piezoelectricity to exist. Now consider a piezoelectric material with the polarization as shown here. And when an electrical bias of this particular nature is applied, then due to the interaction between the internal and the external field, the material would elongate. As you can see, it's quite self-explanatory why the material would elongate. And now consider when an opposite polarity is being applied because of the like charges, it will compress itself. Now consider the case when a mechanical input is being given, that is, the material is stretched along the horizontal axis, then there is a change in the extent of polarization, which means that there is a charge generated on the surfaces of the piezoelectric material. So either way, depending on if you compress it or elongate the material along the particular axis, different kind of charges get generated, as you see over here. Thus, it can be seen that from this deformation of the materials that it is sensitive to the polarity of the mechanical or the electrical input. Now let us start to analyze piezoelectricity from a thermodynamic point of view. Consider a constant temperature environment and analyze the electrical and the mechanical domain. And under each of these domains, these are the three parameters each that we will be interested in. And there are different kind of relationship that we use in this particular thermodynamic analysis, the D form, E form, G, and the H. In this study, we'll be mainly looking into the D form only. Consider a piezoelectric material sandwiched between the electrodes. Now, when an electric field is being applied into the material, due to the indirect piezoelectricity, there is a strain that is being generated, which is corresponding to the displacement pattern. Now, this proportionality constant is the D coefficient of piezoelectricity. Now, when there is deformation, there is corresponding charge that gets generated, right? So that is mechanical to electrical domain energy conversion, and we see an equivalent charge on the surface of the electrode that is generated. And even in this one, the proportionality constant is the D coefficient. However, it is important to remember that here we are dealing with reduced tensors. It is important to notice that even though the piezoelectric coefficient is the same, in one of the form it is the normal one and the other one it uses the transpose. So for all the calculations that we do in these kind of matrices, it is quite important to notice, are you using the transpose form or the non-transpose form? So let us take a step ahead and then look into the energy analysis. So the change in the Gibbs free energy of a system can be attributed to the variations in the thermal, mechanical, and the electrical energy. So this equation shows the case where the temperature, stress, and electric field are so as you see, temperature, stress, and electric field are the control variables. Since we are dealing with variations in multiple parameters, each of the output are linked to the variation of the parameters in the distinct domain. Right? So the first equation here reflects the change in the entropy due to the variation in temperature, stress, and electric field. When you look closely, you see that the term over here is nothing but the heat capacity relationship. Now, this particular equation over here can be further expanded as such and such. This one is the change in strain. This is the change in the electric displacement. Now, when we look into these terms, this is nothing but the relationship between the strain and the stress depicted by the Hooke's law, and this is the relationship between permittivity, electric displacement, and the electric field. Now, when you look closely in these equations, what we see is that we see the piezoelectric relationship emerging. That is the change in strain due to an applied electric field and the change in electric displacement due to an applied mechanical stress. So these are the direct and the indirect piezoelectric coefficients. And here what we observe is the pyroelectricity relationship emerging. That is the change in the charge due to change in temperature. So this can be analyzed as multi-domain interaction where we have mechanical and electrical interactions named as piezoelectricity, the thermal expansion, the mechanical and the thermal domain coupled through phenomena such as thermal expansion and piezocaloric effect, and the electrical and the thermal domain related through pyroelectricity and electrocaloric effect. So let us move over to the next section. Now, to design a resonator in the best possible manner, it is important to know what coefficients are involved in the respective modes that you're interested in, and also what are the non-zero coefficients. So to understand them, let us have a look at the transverse, longitudinal, and the shear coefficients. Consider a 4M crystal. So 4M crystal has a four-fold symmetry. That is, for every 90 degree of rotation, the crystal repeats itself, and it has two sets of mirror plane here, shown using the x and the y axes. For this particular study, this is the common D matrix. And in this particular example, we are looking into the ABO3 perovskite structure, where the polarization is being indicated as here. Now, consider the case where we are analyzing a transverse piezoelectric coefficient, where we apply a mechanical stress along axis 1, and we're trying to collect the charge across the axis 3. Now, when a mechanical force is applied across axis 1, we see that there is a change in the particular arrangement of the atoms, right? So that means that there's a net charge generated on the surfaces of interest, which is along the axis 3. Hence, when there is a compressive or tensile stress that is being applied along this axis due to the movement of this particular atom, which is responsible for the non-centrosymmetric or nature of the crystal, we get charge on the top and the bottom surfaces. And hence, D31 coefficient cannot be zero in this particular class of material, and it is known as a transverse coefficient because we are applying stress along one axis, collecting the charge across the orthogonal axis. Now, considering the crystal symmetry, we can see that D32 coefficient will also be a non-zero value. Now, consider the case where the applied mechanical stress is along the same axis and the charge is also collected along the same axis. And here we look at the D33 coefficient. This is the matrix that we know over here. This is the phase that we are looking into. And applying a mechanical stress along the z-axis, we are pulling the material. We see that this particular atom displaces, generating charge on either surface of the material. That means if you're either compressing or you're applying either compressive or tensile stress to the surface, there is a displacement occurring in this particular axis, and hence charge is collected on the either surfaces. Hence, the D33 coefficient cannot be a zero value for this particular crystal structure. Now, consider a case where we are looking into the D12. Okay, that means that we are applying a particular stress along one axis and we are trying to collect the charge along the axis 1. So what we see is that the displacement, this particular displacement does not create any charges, and hence D12 and D21 coefficients will be 0. And also this particular analysis can be extended to D13, D23. Then you can see that the application of the stress do not create any charges on the surfaces of interest, and hence we are not able to collect any charges, leading to these coefficients being 0. Shear coefficient is yet another important one. For example, we consider the crystal here. This is the surface we are interested in, and this is the stress distribution that you can see over here. Consider and sigma 3(2) being applied onto this material, that is, it is being given a shear force. Then what happens is that the polarization angle changes, which thereby results in a certain charge generated across the surface too, and hence D24 coefficient is also a non-zero value. Similar study can be extended for D15 as well. But when we do that for D36 coefficient, we'll see that due to the crystal symmetry, there's no charge generated, and hence this is also a zero valued. So this is how you can analyze whether a particular piezoelectric coefficient will be 0 or non-zero. Okay. So next, let us move over to the piezoelectric materials that would be considered. So for high frequency applications in the gigahertz, we use aluminum nitride, which is a both-side structured material, and it has been a common choice because it has a stable response without having the risk of depolling. For example, PZT material has a risk of depolling, but aluminum nitride doesn't much. So aluminum nitride exhibits high thermal conductivity for an electrically insulating material and is thus suited for filters, especially in the transmit line. So as many nitrides, aluminum nitride has stiffness coefficient, large stiffness coefficient, and hence they can reach in the gigahertz range. So for example, aluminum nitride is a very light because it's just aluminum and the nitrogen atoms involved. The relative dielectric constant of the material is just 10 or 11. That means it has very low parasitic capacitance, and hence it is very easy to scale up into gigahertz range, and that's why we have a very successful FBAR industry due to the higher electromechanical coupling, low parasitic, low permittivity values, low loss nature of aluminum nitride. Furthermore, because of the higher mechanical, because aluminum nitride is a hard material with light atoms, as I mentioned earlier, and also it exhibits high mechanical quality up to very large microwave frequencies. And moreover, it is CMOS compatible, which enables to achieve monolithic chip integration possibility. Now, lead zirconate titanate, commonly known as PZT, has been widely used since multiple decades in the bulk material scheme, and since more than a decade, it has been investigated in the thin film as well. As can be seen here, we can see that the transverse piezoelectric coefficients are a great function of the material composition, that is the zirconium-titanium ratio. The material property is also heavily dependent on as to how you deposit the material. CST and sputtering are the common methods, and you can see that the properties are quite dependent on the deposition scheme as well. The PZT material is ferroelectric, which means that the polarization state can be tuned by applying an external bias. So this helps to tune the motional parameters of the resonators. Now, as we can see over here, DC bias is actually changing the response of the device. Tanaka's group has reported development of epitaxial-like PZT, which exhibits lower permittivity while still exhibiting larger electromechanical coupling coefficient. The PZT has been used for filter implementations because it offers low motional resistance. Okay. However, the problem with this PZT is that it suffers larger loss at higher frequencies, and also because it has lead in it, it is actually not favorable for CMOS community, and hence we cannot push it for CMOS integration. Lithium niobate is one of the most commonly used materials in PiezoMEMS arena as well. It is highly anisotropic material as the wave propagates differently for different cuts and different orientation of the material. So LN exhibits extremely high coupling coefficient, and hence large bandwidth devices can be fabricated using lithium niobate. And as you can see that the performance of the device can be enhanced by device geometry engineering. We won't be discussing that here, but it will be discussed in depth in the next section. Shear horizontal surface acoustic wave has been based resonators has been demonstrated by this group, which exhibits a very large coupling coefficient close to 35%. So this has the potential to be a very wide bandwidth filter, and as you can see, it's already in the gigahertz range, so it is potentially used for RF communication. Lithium niobate is also a commonly used material in optics. This is an interesting work where higher order Lamb wave modes have been explored to reach frequencies beyond 20 gigahertz. Now, this opens up applications in a relatively new unexplored frequency scale for MEMS devices. This slide will briefly go over the next three materials. So first we'll go through zinc oxide. Zinc oxide also has been widely investigated but has lost its traction in the recent years. Although structurally it is similar with aluminum nitride. Unlike aluminum nitride, zinc oxide is not CMOS compatible. Zinc oxide suffers from leakage issues, and also it's not very ideal for high frequency applications. It suffers from chemical instability. However, we have lots of work which shows its potential for gigahertz application, as you can see over here, and zinc oxide is also being explored for its nonlinearity feature. GaN is a 3-5 semiconductor material which has a large energy band gap, making it an outstanding material for high power and harsh environment applications. The high Q and monolithic integration capability of GaN makes it an ideal candidate for low phase noise, timing, and reference applications. Recent works have demonstrated hafnium zirconium oxide resonators with the operation frequency ranging from few kilohertz to several gigahertz. And hafnium zirconium oxide can be engineered at atomic level to tailor the electromechanical coupling coefficients using schemes such as doping. So this new material, this is relatively very new, and this will enable exploration of nano electromechanical systems, which can then be used for high resolution resonance sensors and spectroscopy applications, etc. Now, to meet the increasing fabrication demands of the PiezoMEMS across the globe, several companies has provided multi-user MEMS platforms. Some of them are MEMSCAP, Silterra. Silterra provides both CMOS MEMS integration solutions. TSMC is developing PiezoMEMS technology. The others are CEA-Leti and Syntef. Some of the applications of the devices fabricated using MEMSCAP platform are energy harvesting and mass sensor, as you see over here. Frequency comb is a very interesting nonlinear phenomenon, and we have used the MEMSCAP to realize extremely high quality factor resonators. Now we shall move over to the second part of the tutorial. The second part contains the following topics. So we'll start with single and multi-port resonators, move over to resonant modes, and then we shall describe the various device performance enhancement techniques, and then go over my research topic, which is support transducer topology. Now let us start with single and multi-port resonators. So in this tutorial, I won't be going much into the transfer function and the equivalency derivation details. However, let us look into these equations, which are the very standard way of representing a single resonant peak system in the mechanical domain, and this is in the electrical domain. So this table shows the equivalency of the different terms in the mechanical and the electrical domain, which most of you would be very familiar with. The equivalent circuit of a transducer can be drawn as such in a very general form, where you give an electrical input to the piezoelectric material, which is a transducer. It converts to the mechanical motion. So the dynamic behavior is modeled using the dynamic arm. It's also known as a motional arm. The equivalent terms in both the domains have been listed over here. As most of the resonators, as most of the systems in applications uses resonators in a two-port configuration, a simplified two-port representation of a resonator has been shown. The highlighted elements are known as the motional components of a resonator. Now, as a piezoelectric resonator, we know that it can be operated under single and multi-port configuration. This slide quickly summarizes the different parameters associated with the measurement. So when the drive and the sense is performed on the same electrode, it is known as one-port measurement scheme. The parameter used to analyze the resonator performance is basically the S11 parameter when you measure using a network analyzer, and it is known as the return loss. And all the dips that you see, this is from an H-bar paper, so all the dips corresponds to the resonant mode. And it is important to notice that many researchers use one-port configuration to extract the electromechanical coupling coefficient of a given mode. This is a two-port resonator scheme where distinct electrodes are used for driving and sensing purposes, and thus the parameters associated with two-port measurement includes a return loss and also the transmission. So particularly here is shown the transmission plot. So as you see, at resonance is maximum transfer of energy, and here you can see a peak in a two-port transmission plot. This is a four-port resonator schematic where you use different electrode combination according to the strain profile of the mod to get an optimal performance. For example, reducing the feed-through level. So this is a measurement result where we have explored differential, two-port, and common drive and sense scheme, and we see that for this particular resonator and the mode of interest, the differential configuration was able to enhance the motional signal and also reduce the feed-through level, thereby enhancing the stop band rejection to a very high value of close to 35 dB. So next we shall move over to the resonator figure of merit. So figure of merit is used to compare resonators operating in different frequencies and different transduction scheme. So this is a common basis of comparison. So FOM, one of the figure of merit is the product of coupling coefficient and the quality factor. The other figure of merit is the product of frequency and quality factor. So the electromechanical coupling coefficient is a measure of the transduction capability of a device under a given mode of interest, while the quality factor is the ratio of the energy stored to the energy lost. Ideally, it is good to have higher value of electromechanical coupling coefficient and also the quality factor. So in this slide, we will basically go over how to extract these values from measurement. First of all, it is important to identify the resonance and the anti-resonant frequencies. And this is the equation that is used to get the KT square. And similarly, using the resonant frequency and the 3 dB bandwidth information, quality factor can be calculated. The value of the static capacitance T naught is your geometry dependent, and it can be calculated once the device area is known, that is the overlap area and also the thickness of the dielectric and the relative permittivity of the material used. So using these parameters, that is KT square, C naught, F bar, and Q, we will be able to calculate the motional parameters, that is RM, LM, and CM. Using these parameters, all the terms of the electrical model of the resonator can be calculated, and this is critical to implement systems such as oscillators, filters, etc. So next we shall move over to an overview of different resonant modes. So before moving into the resonator mode analysis itself, it is important to familiarize with the two terms that are commonly used. One is the eigenfrequency and the eigenmode. So in this particular slide, please note that I'm not going into details of the resonator modes, and also only generic equations are given and common resonator mode shapes are shown for a given category. So this is a flexural mode, which is classified as a bending mode generally and features a large displacement in the transverse direction to the plane of the device. And it is most of these flexural modes depends largely on E3 ones. There are flexural modes where people use E33 coefficients as well. A contour modes occurs where there's a longitudinal standing wave formed within the resonator structure. Right now over here, you're seeing a length extension mode resonator, and this is a width extension mode resonator, as we quite clear from the mode shape itself. So there's another category of mode which are used to go into extremely higher frequencies from megahertz to gigahertz, and they are the plate wave modes. Here we are showing the lamp wave modes only. Surface acoustic wave are basically Rayleigh wave modes, where the surface, that is the surface of the material, it's the place where the wave propagation happens majorly, and along the thickness, the wave dies exponentially. These are the shear modes, which are also used in the megahertz to gigahertz range, where the shear modulus of the material determines the operational frequency, among other things. The shear modulus determines the acoustic velocity. The acoustic velocity of the mode. Thickness extension mode is another important one, as I mentioned in my first slide. This is the mode that is used for F-bar application, which is actually dominating the filter industry. So this is depending on this mode, particularly depends on the E33 coefficient of the piezoelectric material. And it has extremely low motional resistance, high coupling coefficient, hence it can have a very good bandwidth of filter with lower insertion loss. Okay, so in the next section, we shall learn about the different schemes that are used to enhance the quality factor and also the electromechanical coupling coefficient. So the figure of merit, as we mentioned in the previous slide, depends on these two parameters, right? The electromechanical coupling coefficient and the quality factor primarily. So as a PiezoMEMS designer, to know, it is quite important to know the different schemes that you can use and deploy at different circumstances to improve the device performance. In this particular slide, what I'll be doing is I'll go through the two schemes that are generally used in resonators. Then a conventional piezoelectric MEMS resonator, a piezo material is stacked between the top and the bottom electrodes. Such configuration has the following merits, where that is, it has higher coupling, lower motional resistance. If you have just aluminum nitride between two metals, then because aluminum nitride has higher acoustic velocity, like we mentioned earlier, it can be scaled to gigahertz range without much of a problem. But the problem happens where high power is being injected into the system. The resonator goes into nonlinear region. Now that's partially because of the low thickness to volume ratio of the resonator stack, and also the non-ideality of the crystal structure of the materials involved, that is the metal and the piezo material itself. To overcome this shortcoming, an improvised configuration is used. That is, a thin film that we see over here is placed over a low defect material such as silicon. So this is known as the TPOS scheme, that is thin film piezo on substrate. So here it features better power handling and higher quality factor, but now due to the loading effect, we will start to see a little increase in the motional resistance and decrease in the coupling coefficient. So this is an experimental result where we can see that when there is no silicon, the device goes into nonlinearity at even for -5 dBm power. But when there is silicon associated with it, even for +10 dBm, it is fairly linear. This is the case. Please note that this is aluminum nitride, which is higher acoustic velocity than silicon. And so that's why there's a decrease in the resonant frequency. Now consider a material such as PZT. When PZT is being used in conjunction with silicon, we can see increase in frequency. Why? Because silicon has higher acoustic velocity, and because silicon has really high Q, it will boost the overall performance of the device. Hence, lower motional resistance and higher Q. So this is how we can engineer the device performance using an additional substrate. Next, what we will be looking into is known as the phononic crystals. So here we shall discuss about engineered geometries that can have acoustic deadbands. This concept is basically known as phononic crystals, as the heading itself says that. The PNC, also phononic crystals, are traditionally used in MEMS as attenuators. Now, what does that mean? So this is a unit cell of a phononic crystal, and this is the frequency band diagram. As you see that this particular phononic crystal can have dead bands, right? That means that, which means that the frequency range, it's a frequency range where the acoustic energy transmission across the cell is minimal or ideally non-existent. And hence they can be used to terminate an active resonator onto the substrate. So this is the FEM result, and we can see that when it is like a conventional termination to the substrate, there's energy leakage. But then when you use a phononic crystal with such that the resonant frequency falls within the dead band, because there is no acoustic energy transmission possible, there is no energy leakage. This is the fabricated device. So let us look into the measurement to see how exactly the Q is improved. So this is the device Q without phononic crystal, and this is the Q with phononic crystal. We see close to 4 times enhancement in the quality factor. This is the case where, This is the case where PNC is used to terminate the device, right? Now, let us see how PNC can be used as frequency selective couplers. In the first example, the PNC is used to attenuate the coupling between two resonators. As you see over here, without PNC, there's larger coupling. With PNC, there is lower coupling. Whereas in the second case, the PNC is designed such that the coupling between the two resonators is such that, so for the first fundamental frequency, the PNC has a dead band, whereas for the third harmonic, it does not have a dead band. Hence, it couples the energy from the fundamental to the third harmonic. In this section, it's a little different. We'll deal with the lateral dimension and also the electrode designing aspect. To enhance the quality factor and also to eliminate the spurious mode. So spurious modes are unwanted modes that are present around the frequency of interest. So let us begin with the lateral geometry engineering technique. The first work compares a regular geometry and a convex structure. As can be seen from the displacement FEM, that the regular geometry has larger displacement in the periphery, while the engineered geometry has close to zero displacement across the periphery, which means that the anchor loss is lesser for this particular design, and hence the quality factor is also much higher. So for traditional design, the Q is 900, whereas for an engineered device, it is 14,000. This is another study which banks on the acoustic energy dispersion. So this device has been engineered such that it has varying width along this resonator geometry. The end result is that the majority of the energy is confined in the central region of the resonator with minimal seepage of energy towards the anchor. So there are two methods that are being investigated. One is the abrupt change in the geometry periphery. The other one is the gradual change in the periphery. So this work also reports devices that are operating in the higher frequency regime, such as 80 megahertz, and quality factors close to 20,000 has been attained, which is quite remarkable. So these particular two studies are what enhancement in the quality factor. Now, next one will be looking into how can we eliminate these kind of spurious modes that comes close to the resonant frequency. So one such approach is the apodization technique, which is commonly used in store resonators. So we can see that by merely changing the weight of the electrode layout, we are able to eliminate the spurious mode. As you can see in the measurement results, the apodized resonator, that's the red trace, eliminates the spurious mode. This is quite critical for applications such as filters. In the next section, we will investigate. Again, we'll go back to the quality factor study, how the peripheral design of the resonator can be enhanced, can be designed or improved to increase the quality factor. So this work is a combination of a reflector and also how to change the theta length. So various studies have been done by changing the distance of the reflector and also the theta length to see how the acoustic energy reflection happens. So as you can see that it is quite a periodic nature, which means that it is a function of the wavelength of the resonator as well. So FEM studies were done, and then it can be seen that there is a huge improvement in the quality factor by optimally designing the resonator. So in addition to the reflector and the theta length design, then the advanced stage was adding a notch to the resonator. So this is a measurement that compares what is exactly the impact of this engineering. So this is a traditional resonator, right? There is no reflectors, no notches, nothing. The Q is just 1,500. Now add a reflector, you boost the Q to 11,000. Add a notch with the reflectors, then the Q goes to 20,000. So this is a huge engineering advantage. That is, you do not add any extra power or any fabrication complexity, but by mere acoustic engineering, you're able to boost the performance of the device. So far, we have looked into the quality factor enhancement. Let us look into the electromechanical coupling engineering as well. So here we have three ways in which the electrodes are being configured. Here, the bottom electrode is present. and it is being grounded. So this is how the capacitance distribution looks like, or the electric field, sorry, distribution looks like. This is the capacitance combination. Here the floating, this particular bottom electrode is floating, and this is the capacitance relationship. Here is an external field that you see, it's an extra field that you see. And here you do not have a bottom electrode, and hence it is known as a bottom surface condition. And you see that for these three particular electrical boundary condition differences, the device performance changes vastly. So for the case where it is where there's an open bottom surface, the quality factor is high because there's no metal involved in the bottom, but the coupling coefficient is low. On the contrary, the lamp wave resonator with a floating bottom electrode has a higher coupling coefficient. Now, when there is a grounding because of the static capacitance coming into play, the effective coupling coefficient drops. So this particular result or the studies shows how we can engineer the electrical boundary conditions, thereby changing the electrical field distribution between the electrodes to get different electromechanical coupling coefficient. Now this work that is shown over here shows how you can change the bottom electrode coverage. So as you see, this particular area is being modulated and we can get different coupling coefficients. Here is just the material property itself, where you can orient your device along different axes to get different coupling coefficient. For example, to get a very wide bandwidth device, orient along this particular axis. For very small bandwidth applications, you can choose this particular angle as well. So in the next section, we shall move over to a new topology in piezoelectric MEMS known as the support transducer topology, which is my main area of research.